In this video, I just want to go through a few examples. So a couple that are a little bit more complicated and involved than the ones that we've been doing. So our first one, I'm going to have iron 2 plus reacting with MnO4 minus going to manganese 2 plus iron 3 plus. And the first thing we're going to do is we're going to balance this. And we'll do it in acidic solution. So remember, when we're balancing these, we're going to split them into half reactions. So I'm going to have my iron going to my iron, so that's going to be one of my half reactions. So Fe2 plus going to Fe3 plus. And then our next step was to balance that for all atoms other than oxygen or hydrogen, which this one is, and then balance it for oxygen and hydrogen, which I don't have any. We're then going to add electrons to make my charges equal. So I have a +2 here, I have a +3 here. So if I add 1 electron to my product side, I now have a net charge of +2 on both sides. My second half reaction is going to be my manganese compound going to my manganese ions. Manganese is balanced already, so now we need to balance my oxygen. Remember, if we're in acidic solution, we can add protons and or water wherever we want. So because I have 4 oxygen on my reactant side, I'm going to add 4 water to my product side, and that gives me 4 oxygen. That also gives me 8 hydrogen. So I need to go over here and add 8 protons. My next step was to balance my net charge. So here I have a +2, right? There's no charge here and there's a +2 charge here. On my reactant side, here I have 8 positives and 1 negative, so that's a +7. So a +7 charge right now. Here I have a +2 charge. So to make those 2 electron counts equal, or sorry, make my charges equal, I need to add 5 electrons to my reactant side, right? If I have now 5 negatives, I have a +2, so +2 on both sides of that equation. My next step then was to get the electron counts on my 2 half reactions equal. So I have 1 for my first half reaction, I have 5 for my second half reaction. So I'm going to take this entire top equation and I'm going to multiply it by 5. And now I have 5 electrons for both half reactions. Also remember, one of our places to check is that one of my reactants, right, needs to be my half reaction for the oxidation step. So I need to have my electrons on my product side. My other half reaction is my reduction half reaction, which means I need to have those electrons on the reactant side, right? We're adding them. So this one here was my oxidation. This one here is my reduction, right? Remember, my oxidation, this would occur at my anode. My reduction would take place at my cathode. So adding these together to get my balanced equation, my 5 electrons are going to cancel, and I'm going to have 8 protons plus MnO4 minus plus 5 iron 2 plus going to Mn2 plus 4 water plus 5 iron 3 plus. So that would be my balanced equation for this reaction. So what we're going to do next is we're going to calculate the pH of our solution. So calculate the pH of the solution at 25 degrees Celsius when the concentration of iron 2 plus is 0.25 molar. Our concentration of MnO4 minus is 0.30 molar, my concentration of iron 3 plus, 0.050 molar, and my concentration of manganese 2 plus, 0.010 molar. And then our cell potential for this problem is 0.67 volts. And then I'm just going to give us our standard cell potential also. We could calculate that using our table of standard reduction potentials, which might be a really good thing for you to do. Pull out your table, find these two on there, make sure you reverse the sign on the correct one, and see that you can get this answer. So our equation, let's just kind of try to figure out how we're going to get pH from this, right? I know that I have a cell potential, I have a standard cell potential, I have concentrations, I have a temperature that is standard. So the equation that we can use is this one. And then the log of Q, right? Q is our reaction quotient. We know that we are given the concentrations, right? If I was to set up Q, and we will set up Q, it's going to be the concentration of manganese ions multiplied by the concentration of iron 3 plus raised to the 5th power, right? Those are both aqueous. Water is a pure liquid, so I don't need to include it. And then that's going to be over the concentration of my reactants, also raised to powers equal to their coefficients. All of those are aqueous. And we're given the concentration, right, of all of these ions, but we're not given the concentration of my hydrogen ions. And we do know that pH, right, is the negative log of those hydrogen ions, right? Remember, hydrogen ions in water, right, in aqueous solution are hydronium ions. So essentially what we're going to do is we're going to use this equation, we're going to solve for Q. Once I get Q, I can plug all of these numbers into my expression, solve for the one that I don't know, take the negative log of that, and I'm going to have my pH. So kind of first step, let's solve for Q. So plugging in all these values, I have that 0.67 volts is equal to 0.74 volts minus 0.0592 volts. And then the number of moles of electrons transferred is 5, so over 5, multiplied by the log of Q. So let's just get Q. So I'm just grabbing my calculator here and typing this in. You need to take the anti-log base 10, so 10 raised to the value. And I get a really big number. I do only want a couple sig figs right now, but I'm going to carry them all out and then just round when I'm done. So I'm just going to underline this to remind myself that I just want 2 significant digits. So we're now going to set up our expression for Q. And I'm just going to go copy this equation down so I don't need to scroll so much. So I just want to have it a little bit closer here. So I know that Q is going to be, right, the concentration of manganese 2 plus. It has a coefficient of 1, so we're going to raise that to the 1st power. That's going to be multiplied by the concentration of iron 3 plus. It has a coefficient of 5, so we're going to raise that to the 5th power. Remember, we're excluding water. Water is a pure liquid. Its concentration doesn't change as the reaction proceeds, so we're not going to include it. And then that's going to be the concentration over the concentration of hydronium ions raised to the 8th power, right, because I have 8 moles, multiplied by the concentration of MnO4 minus, and then the concentration of iron 2 plus raised to the 5th power. So we're going to then plug in all of our values for those. I don't need this anymore, so I'm just going to get it out of the way. Those values were all given to us here, right, with the exception of our unknown. So plugging all of those in, I have 8168887. Again, we're just keeping track of our significant digits, is going to be equal to 0.010. I am just dropping my units, right? Remember, equilibrium constants and reaction quotients have units. We don't generally show them, so I am just going to drop them. I do know that this is going to be molar when I'm done. Concentration 0.050 raised to the 5th power over my unknown raised to the 8th power. 0.30 and 0.25 raised to the 5th power. So now that I've got everything plugged in, I'm going to grab my calculator. So just do be careful on the math on this. And I got that my hydronium ions raised to the 8th power still is equal to 1.3 times 10 to the negative 11th. And I am going to double check that real quick. Hopefully you guys are typing all this into your calculator also. There's a lot of places to goof up typing it in, so. Okay, I got the same number. So I do need to take the 8th rid of both sides. So I'm going to essentially raise 1.3 times 10 to the negative 11th to the 1/8 power. And when I do that, I get that my hydronium ion concentration is equal to 0.044, just rounding for sig figs here, and then my pH is going to be the negative log of that number. And I am keeping it all in my calculator. I'm not actually taking the negative log of 0.044. I'm actually taking the negative log of the number in my calculator, so 0.043599 and so on. So if you are like clearing it in your calculator and typing it in fresh each step, you may come out slightly different than me. And then just remember our log value rules, right? I want 2 digits or 2 sig figs, so 2 digits after the decimal point. So I got 1.36. What we're going to talk about next are pH meters. So if you were in lab and you had a solution and you wanted to determine the pH of it, one of the ways to do that is to use a pH meter. So with a pH meter, you actually have a probe that you put into your solution and then it measures the pH for you. So it'll give you a readout of its pH. And pH meters are really just an application of the Nernst equation. And our anode in our pH meter is going to use the hydrogen half reaction. And I'm writing down hydrogen electrode, but again, we know our electrode actually needs to be metal, so it's going to be usually platinum. So a lot of pH meters will have a little strip of platinum in them, and that's what we're using as our electrode. And then our cathode is going to be a reference. The different pH meters are going to have different reference electrodes. And after we derive our equation here, we'll do an example, and I can show you an example of what can be used as our reference electrode. In our hydrogen electrode, I do want to note that the hydrogen gas is at 1 atmosphere. They are sealed so we can keep the pressure of that gas constant. We know that our cell potential, right, is going to be equal to my cell potential for my oxidation half reaction, right, which is going to be my anode, plus my half reaction, right, my cell potential for my reduction half reaction, which is going to be that reference, right? My anode, again, is my oxidation. My cathode is that reduction. So what I want to focus on here first is just talking about this part, just this oxidation. So everything I'm going to write below here for a little bit is just talking about that hydrogen electrode, right? And that hydrogen electrode, let's actually write it again. And again, I keep saying hydrogen electrode, but remember the electrode itself is platinum, so the hydrogen half reaction. If you were to look this up on the table of standard reduction potentials, right, it's going to be written as a reduction. So you would have the 2 hydrogen ions plus 2 electrons going to hydrogen, and then my cell potential for that is 0 volts. It's still going to be 0 volts, but I do have to reverse it, right, to get the oxidation. So this is my half reaction for my anode. And then remember, when we reverse the reaction, we reverse the sign, but the reverse of 0 volts is still 0 volts. So, right, my standard potential for my oxidation half cell, right, is 0 volts. So the equation we're going to use for this is my cell potential is equal to my standard cell potential. We are going to use the version of the Nernst equation where I'm at 25 degrees Celsius, and then this is the log of Q. So plugging some things in, I know that this is going to be 0 volts, right? We're talking about my oxidation half cell, which is using my standard hydrogen electrode, so 0 volts. So I'm going to substitute in a 0 for this number. I know that I have 2 moles of electrons being transferred, so N is going to be equal to N is going to be equal to 2. And then Q, if we look at Q a little more details, right, Q is going to be the concentration of products raised to a power equal to its coefficient over the concentration of reactants. This is a gas, so gases are included, right? It's pure solids and liquids we exclude, but gases and things in aqueous solution are generally included. And since it's a gas, we could use partial pressures instead of concentration. But I know that my partial pressure is 1 atmosphere. So essentially what I have is just 1 on the bottom, right? If I plug in my partial pressure, I'm going to plug in 1, and then anything over 1 is just equal to itself. So this is what Q is going to be equal to. So we're going to plug this in for Q. N is going to be equal to 2. E naught is going to be equal to 0. So we're going to rewrite this here. E is equal to negative 0.0592 volts over 2. And then that's multiplied by the log of hydrogen ions squared. And then using a log identity, right, I know that the log of something squared is the same as 2 times the log of whatever that thing was. So I'm going to rewrite that using that identity. And then my 2's here are actually going to cancel each other out. And then I'm going to redistribute that negative sign a little bit differently. I'm going to move it, and mathematically, right, this is fine, as long as the negative is somewhere over here, I'm going to move it here, right? When I do that, I end up with the negative log of hydronium ions, which is equal to pH. So I'm again going to move this negative over, which is going to make this equal to pH. I'm going to substitute pH in then. And I'm going to get that my cell potential, and again, this is the cell potential just for this oxidation, right? We're only working on this oxidation side. My cell potential, we can put the OX there just so we don't forget, is going to be equal to 0.0592 volts multiplied by my pH. I'm now going to take this, we're going to go back up, and we're going to plug it in for this. So I know that my cell potential is going to be equal to the cell potential at my oxidation half cell, which is equal to this, plus the one at my reduction, which is going to be that reference. So I'm putting REF for reference. You could put RED for reduction. I know that my reduction, right, that's my cathode, is going to be my reference. And then I'm just going to rearrange the sulfur pH, because that's what we're trying to do with the pH meter, is sulfur pH. So just rearranging this equation, I have that pH is going to be equal to my cell potential minus my reference half cell potential divided by 0.0592 volts. And then this is the equation that we're going to use if we're using a pH meter that uses my hydrogen electrode as its anode to determine our pH. So let's do an example using that. So the following cell has a potential of 0.49 volts, and we're going to calculate the pH of the solution in the anode compartment. And you could ignore the in the anode compartment and just calculate the pH. But again, remember this pH is coming from my oxidation, which is my anode. So that is the part that's actually determining our pH here. And then I'm going to give it to us using shorthand notation. And then from that, we'll actually write our equation. So I'm going to have platinum, hydrogen gas that is at 1 atmosphere. When we learned our shorthand notation, I said that sometimes concentrations and pressures are included in the notation. And this is going to be an example where we're going to do that. And then I'm going to have hydrogen ions. This is what I'm going to try to figure out the pH from, right? We don't know the concentration. If we did, we would know our pH because we could just take the negative log of that. And then my cathode compartment is using mercury 2 chloride. Chlorine ions. That's going to be at 1 molar. And then mercury liquid. So this over here is my reference cell. So really, to solve the problem using this equation, we have E cell that's given to us in the problem. This is our half cell potential for our reference cell. So you could just look this up, on your standard reduction potentials, it's already a reduction. Just take that value, plug it into the equation. So let's write that out so we know what we're looking for. So I do have mercury. Remember, we always write our reactants first and then our products second when we're doing our shorthand notation. I know on this one I have 3 things included, right? I have this one and then I have both of these. So I know for sure that this is going to be a reactant because I'm starting with it, but then the question is this a reactant or a product? And you just kind of have to use your brain to figure that one out, right? If I have chlorine here, I have to have chlorine on my product side. I could balance it using acidic or basic solution, but neither one of those provides chlorine ions. The chlorine has to be on the opposite side of this so we can balance it. So it is a product just using deduction. And then mercury. And then if we were to balance this, right, because I have 2 mercury, 2 chlorine, I have to put a 2 here and a 2 here. And then to get my electron count equal, to get my charge equal, I need to put 2 electrons on my reactant side. So this would be the equation that I'm looking for. And if we look that up on our table of standard reduction potentials, it has a value of 0.268 volts. If we were to look at our complete, let's just do this for practice. We don't really need it to solve the problem, but it's really good practice for us. If we were to write our entire cell reaction, write our net reaction, I'm going to have hydrogen gas, right? Reactant, this is my product. So I'm going to have hydrogen gas going to 2 hydrogen ions plus 2 electrons, right? That's my oxidation, that's my anode. So my electron counts are equal when I add those together. So my net equation is going to be hydrogen gas plus mercury 2 chloride going to 2 chloride plus 2 mercury plus 2 hydrogen ions. And then just checking to make sure it's balanced, right? Because we haven't done this in a while. I have 2 hydrogen, 2 hydrogen, 2 mercury, 2 mercury, 2 chlorine, 2 chlorine. And then remember our net charges have to be the same on both sides. So no charge and no charge, meaning I have a charge of 0 on my reactant side. Here I have a -2, no charge, +2. So that gives me a 0 total on my product side. So this here would be my overall cell reaction or net reaction. All right, back to solving our problem. We're just going to take this equation. I'm just going to copy it down so we don't have to scroll so much. And then we can plug in our values. I guess we still have to scroll to get this out of my way. So my cell, 0.49 volts. My reference, 0.268 volts. Divided by 0.592 volts. We end up with volts divided by volts. My units go away, which is what we want because we know we don't have units on pH. So typing these into my calculator. And I end up with 3.7. I'm just double checking my calculation here real quick. Yeah. So watch sig figs. I don't want you guys to do this. So we're not using a log value here to get pH, right? I'm just subtracting and I'm dividing. So there's no weird digits after the decimal place sig fig rule because that's for logs and we're not using any logs here to get our answer. So it's just straight normal sig figs. So 2 digits after the decimal point, 3 digits after the decimal point. So you want 2 digits after the decimal point. So I got 0.222, which you would round to 0.22. And then I have 2 sig figs divided by 3 significant digits, giving me 2 in my final answer. I know for pHs for a really long time we've been saying only digits after the decimal point count, but that's because we were getting them by using logs. Here we're not, so just be really careful on your significant digits.